Okay, what I'd like to talk to you about now is how to, by hand or with a basic calculator, convert a secant line idea, average rate of change, into estimating a instantaneous rate of change, which is the slope of the tangent line. So let's take a look at this situation. Okay, so back to our parabola, y equals x squared. And what I'm interested is finding the slope of this tangent line at the point 1, 1. Now, the tangent line only touches the function at one point, and it exhibits the steepness of that function at that one point. And the slope of that tangent line is called our instantaneous rate of change. Now, we've been talking about secant lines. A secant line is any line I connect between 2 points on the function. And if I have 2 points on the function and I calculate the slope of that secant line, we call that slope the average rate of change. So on this one, what I'm looking at is I've got a secant line and wrong color. The secant line is my orange line. So the average rate of change is the slope of my secant line. I've got 2 points, and I'm just going to take y2 minus y1 over x2 minus x1, and I get 8 over 2. The secant line has a slope of 4. Now, the tangent line clearly has a slope that's smaller than 4. So how could we get this by hand? First of all, we need to visualize what we're doing so it makes sense. Otherwise, the procedure is just memorization, regurgitation, and that's not going to work on the test. So let's get to a visualization. We know as that secant line gets closer and closer, I'm going to remember this is my slope of the secant line, and we just had it at 3, which gave us, right at 4. There we go. So as I move my second point closer and closer, the average rate of change of my secant line is getting closer and closer and closer to the instantaneous rate of change, or the slope of my tangent line. So that slope of the tangent line appears to be pushing 2. And then it disappeared because we went too far. Bring it back from this side, again getting closer and closer to 2 until it disappears, because the secant line disappears when I'm at 1 point. However, let's do this by hand without a computer. So let me get a new screen and just add a page. Okay, our formula was y equals x squared. And we're looking at points. We know how to get points. We're going to use our starting point, which was at 2. So if you're at 2, plug in 2 squared. The y value is 4. So I want to estimate the instantaneous rate of change, which is the slope of my tangent line when you're at that point. So this is what we're trying to find out. What is this? So, secant line. A secant line is when we connect 2 points. Okay, so let's make a couple of estimates using 2 points. Got x's and y values. First x is 2, and we know the y value is 4. We need another point on the graph to connect. So let's try the point at 2.1. Now, I'm going to use my calculator, a little help, but any calculator will work, even if a cheap calculator. Turn it on, and why is it not coming on? There we go. Clear. So we've got x squared, and I'm going to show you a little cool aspect of your calculator. I'm going to, let's see, Actually, let's go 2, we'll use this later, 2.1, I'm going to square it, and that's my y value, and I'm going to write that down, and let me just do something so I can see both of these at the same time, and I'll just move this, there we go. So my y value is 4.41. And what we want to do is take y2, which is that, minus y1, which is 4, and divide it by the change in x. Now notice I chose my change in x very carefully. The distance from 2 to 2.1 is exactly 0.1. So I'm just going to now divide this, my change in y, divided by my change in x, which is 0.1. And this would be the slope of the secant line between these 2 points that are very close together. So the slope of this secant line is 4.1. Now, what we want to do is get our 2 points closer together. So to get our 2 points closer together, let's make the distance between them smaller. So we start at 2, 4 as our first point, and let's make the distance between them 0.01, which means my next x value, remember this is our value h. So our next x value is going to be 2.01. Let's find the y value. 2.01, oops, missed my 0.01 squared. So there's my y value. And I'm going to subtract the first y value. So there's my change in y, and I'm going to divide it by my change in x, which we named h, 0.01, divided by my change in x, oops, not twice, 0.01. And the slope of this new secant line is 4.01. And this is going to be a better estimate of my instantaneous rate of change because my points are closer. H is the distance, and h went down. So my first estimate of the slope of the tangent line was 4.1. My second estimate is better at 4.01. And again, I can make as good an estimate as you would like just by making h smaller. What if I took h and made it 0.001? So let's make our table. First x value and first y value never change. We're looking at the point 2.4. So now my x value is 2.001. And what is my y value? Let's use my calculator. 2.001 squared is my second y value. 4.004001. And I want to calculate the slope now by taking this y value minus the first y value, which is 4. That's my change in y. And I'm going to divide it by my change in x, which we said was 0.001. And there's my new estimate. So I'm just going to move this over a little bit. The slope of this secant line is 4.001, and that's my average rate of change as my points are getting closer and closer together. Notice I wasn't using the computer, doing it by hand. First estimate, 4.1. Second estimate, 4.01. Third estimate, 4.001. And I'm guessing as my x values get closer and closer and closer, that I am now confident that I can make a good estimate of my instantaneous rate of change, the slope of the tangent line, to be approximately, let's use the approximate symbol here because it's still an estimate, approximately have an instantaneous rate of change of 4. So again, I wasn't using a lot of technology, just tables, just calculating y2 minus y1 over x2 minus x1. I was just making my points closer and closer together so that we're now better estimating our instantaneous rate of change.